I would like to present Anders Nordby from Ottawa University and Liquid Geomatic. He will talk about a fully automated method for satellite-derived bathymetry. So Anders, I can leave you the microphone for 20 minutes or so.
All right, great, thank you. Yeah, I will. I'll speak in English if that's okay, and I'm happy to get questions in French as well. I do speak some French, so I can understand questions you will ask me. My name is Anders Knudby. I'm an associate professor at the University of Ottawa, and I also run a very small company called Liquid Geomatics. And over the past, coming up to 2 years now, I've been working on workflow for fully automating bathymetry using satellite imagery. And so that I'm going to present to you its current state right now. The way it works is that it accesses and downloads large number of satellite images from a location that the user picks. It can work with Sentinel-2, both A and B, and Landsat 8 imagery at this point. I picked that imagery because it is free and has fairly frequent revisits, so there's a lot of it available. What the workflow does is it goes on to ESA or USGS databases, and according to a couple of criteria that the user can also set or can leave as default, it finds the imagery that is suitable, so has no more than a certain threshold of cloud cover, is from the right location, maybe the right time of year. If you're in the Arctic, for example, you try to avoid ice and snow. And so it downloads all of the relevant imagery for your area of interest. Then it applies a mask to get rid of all of the things that we don't want when we're trying to estimate bathymetry. So in this example, these are the same images that you saw before, but with red masking out land, clouds. This example is from Australia, so there is no ice or snow. But it also masks out other things like boats. If there's an area with exceptionally high wind and lots of white caps, it's going to end up masking that out too. So essentially all of these things that we don't want to have information on when we're trying to estimate bathymetry. What it then does is that for each image, it runs it through a physics-based SDB workflow. So what that is, it applies some vicarious calibrations to each sensor band. It does an atmospheric correction to get rid of the intrinsic reflectance of the atmosphere. It corrects for specular reflection or sun glint off the sea surface, and then it estimates the depth of water on a per pixel basis based on the spectral reflectance of that pixel. After it has the initial estimate of water depth, it then applies a correction for tidal stage at the time the image was acquired to reference everything to mean sea level. But of course, we could reference it to something else if we wanted to. There's a lot of parameters that go into this particular step, and typically the way it has been done in the past is that an operator will look at the results from the image and just visually see whether it looks like it makes sense. If in situ data are available, you can compare it obviously to the in situ data, and then you can fiddle with the parameters until you get something that either just visually looks right if you don't have in situ data, or that compares well to the in situ data if you have those. So a lot of the time I've spent on this has been to come up with a set of parameters for this particular step that works well on average. Now that's obviously a little bit less optimized than what you could achieve if you had an experienced operator looking at each individual image, but it doesn't need to be because of what happens in the next step, which is where we take each of the individual water depth estimates for each pixel and we merge them into a single ensemble estimate. across these sites. So this example that I've been showing you imagery and examples from so far, this is the island in the middle is Lizard Island. It's in Australia. It has been one of my test sites because I have some good test data for there. And so you can see that all of the clouds and all of the problems in each of the individual previous images is gone now, because here I have picked all of the good pixels from each images and I have created an ensemble estimate based on them. So this looks like it works reasonably well. Lizard Island is also a very kind test site to work on, I'll say, because the water is typically fairly clear. There's a nice lagoon area with nice and bright sandy substrates, and there's some coral reefs and some seagrasses around there. And there's a couple of other reefs that you can clearly see here that are also identified in the bathymetry product. But if you look on the product on the right here, you'll also notice that the, sorry, I should have explained what it's actually showing. So the red areas on the right here, they're masked out because they are land. For the rest of the area, you have the shallowest water in the colors that are closest to red. So the yellows and the greens, and then we go deeper and deeper into the blues. So you'll notice here that sort of roughly in the southeastern portion of this bathymetry estimate, the water is estimated to be shallower than in the eastern and northern part. And that's obviously not true. We can't estimate that because that water is just deep. And so that is an issue, and I'll get into in just a moment how we handle that. But you'll also notice that in general, the reefs are very well outlined. The shallow water in general, if you look at the distribution of depths, you see that channel. I don't know if you can see my cursor, but there's a south of Lizard Island, there is a channel into the lagoon, and the water in that channel is correctly identified as being deeper than the lagoon itself. You'll even notice actually that there's a couple of smaller reefs that are really hard to see in the imagery out east of Lizard Island. But that get picked up in this bathymetry product. So this is actually a slightly old slide now. I started out testing this at 5 different sites. You can see them here. Now I've added a couple of more sites, and I'm continuously working on adding additional sites to build up more experience with this workflow. I have a couple of sites that are really tricky. One is in the St. Lawrence River. One is further up north in Canada. So results from those are gonna come a little bit later. Not in this talk though. So if we look at the actual results, like how good is this workflow at estimating water depth? So you'll notice this is from the Cambridge Bay site. This doesn't look too pretty here. We have in situ validation data. Well, these are airborne LiDAR data, generously provided by the Canadian Hydrographic Service. And then we have, for each of the data points that we get from the airborne LiDAR, we have my bathymetry estimates on the y-axis. And so what we would like is for all of these points here to lie along the dotted one-to-one line, and they clearly don't. So this is something that has stumped me for a while. And stumped my collaborators as well. So we've tried very hard to figure out what part of the physics could account for this problem. And I'll say so far we're not really actually sure. We have some ideas, but none of the things we've tested so far really truly account for this issue. It is an issue that is typical for the Arctic, but when we look at the data for Lizard Island, these are actually, other people have already published STP studies for Lizard Island, and we see the same pattern in those studies, and we see it here as well. The points lie above the one-to-one line when we're at depths sort of between maybe 5 and 15 meters. Not as far above the line at Lizard Island than they do in Cambridge Bay, but they're still above the line, so there is a bit of an issue there. We have found what I will call a hack that I'm not sure is based on sound physics, but that actually works to provide better results from an STP perspective. So once we apply this hack, which takes the form of some additional vicarious gains applied to the different sensor bands. we get this kind of result instead. So I think this looks more reasonable. We certainly get points that fall very close to the one-to-one line up until a certain depth where I'm going to say around maybe 13, 14 meters. And beyond that depth, we probably shouldn't trust the SDB results anymore. And this is a common issue with SDB. You know, when the water gets too deep, there is negligible influence from sunlight reflecting off the seafloor. And when there's negligible influence, we cannot detect it, and we don't know whether the water is 15 meters or 1,000 meters deep based on its color. So an additional thing we do in this workflow is we we calculate some confidence intervals. This is done based on the inversion of the radiative transfer model that we use. So this is, I'm showing them to you here on the graph, but the confidence intervals here that I'm showing with red arrows, they're not actually based on data from the graph. They're an intermediate product of the workflow. So what we can see here, if we look at confidence intervals for different depths in the SDB, for Cambridge Bay here, they're you know, it's a fairly narrow. This is a 90% confidence interval. They're fairly narrow as we move up to deeper and deeper depths. And then as we get up to the really wide arrow here, the confidence interval actually tells us that we should not trust these depths. So these depths where I have the red arrow, the SDB workflow says that they're about 16 meters deep, but it also says that they could be anywhere between 13 and 30 meters. You know, so we know to disregard them. So you can use these confidence intervals to set a threshold. In this example here, I've set a threshold at around 3 meters. If the confidence interval range is wider than 3 meters for a given pixel, we ignore it. We say, no, we actually don't know what the depth is here. And what that does is it serves to effectively get rid of all of the deep water. So we don't make erroneous predictions for it. If we apply the same idea to Lizard Island, we can see that it also works reasonably well at Lizard Island. Although here there is a group of points here, not very many, but there are some that still lie quite far from the one-to-one line. So this is also an area of active research here. So here I have another example. Some of you, who I've talked to in the past that will have seen this example before, but you have an image here from the Astronomical Society Islands in Canada, where you can see near the middle of the image, there is a slightly brighter part of the water than what it is surrounded by. And this is where we had a grounding in 2018. If we look at taking this image, oh yeah, there's that shoal. If we take this image and we run it through the workflow, along with all the other images that are suitable for this area, we get this result here. The color scheme on the right here is the same. Red identifies things that are masked out. In this case, these are the islands. And then we have shallow water in yellow and greenish colors and deep water in blue colors. And we clearly see the green color showing here that there's a shoal here. So obviously at this point, after the grounding, that shoal has been nicely mapped. But as you'll notice with all of the yellow circles here, there's a bunch of other shoals in the area. And if we compare to the current chart of the area, those have not been mapped. So I think there's potential for this kind of analysis to highlight at least discrepancies between what we see on the official charts for this area and what we see in the satellite imagery. And to do so in a way that's easier than for someone to have to look at all of the imagery manually. Here I have another example. This one is from an area in Western Hudson's Bay where you can see, just looking at the imagery, there's a lot of shoals here. There's a lot of islands and there's a lot of shoals. This is not a high traffic area, but it's probably still worth figuring out where there's navigable water and where there isn't. So if you apply the workflow to this area, we get what we see on the right here. And again, the workflow very nicely outlines lots and lots of shallow water areas. And if we apply the threshold that I talked about before, that's based on the confidence intervals, to this, we actually can create some polygons, in this case, that outline all of the areas we know to be shallow. We may not know exactly whether a given pixel is 5 or 6 or 7 meters deep, but we know it's not 30. We know it's shallow enough that we get sunlight reflecting off the seafloor, enough that we can detect it in the imagery. So this is sort of the state of this workflow right now. It provides a per pixel estimate of depth with an associated uncertainty interval, and it provides these kinds of polygons that outline areas that we know to be not deep. That is my show.